about the median, median mode and the standard deviation, and how you can find out the standard deviation. Just a short one problem on the standard deviation. This is pretty um, common problem. So I'll find mean and standard deviation of first in natural numbers. Right? So of course, a few equations are formula are required. Right? So one formula is important is that if we add first in natural numbers, the formula is n into n plus 1 by 2. And if you add the first in natural square numbers, the formula is n into n plus 1, 2n plus 1, right? 6. This is 2 are required here. The formula wise, it is quite easy. First, for the mean, x bar would be 1 by n summation of I1 to n of xi, that is nothing but the 1 by n 2 plus 3 to n. We take the help of the first example formula. So 1 by n multiplied by n into n plus 1 by 2. So this one, so it will be n plus 1 by 2. Now, for the variance again formula, so this is nothing but the application of the formula. So this case we are going to use the second equation, though we are doing some algebraic kind of thing, but still the second formula would be useful here because this is easy to find out in terms of that case, because this is nothing but 1 square plus 2 square plus n square minus x bar already we know, so n plus 1 by 2 whole square. Okay. So this is again the previous formula we are going to utilize. So it will become n into n plus 1 to n plus 1 by 6 on so here both the cases I can find out that n plus 1 by 2 is common. So let's take up n plus 1 by 2 as common and simplify the whatever there inside this. So we do a linear algebra. N plus 2 minus 3 and minus 3 6. So minus 1 by 6 square minus 1 by 2. So this is your variance. Square root would be your standard deviation. So this is more or less application of the formula of the standard deviation of variance and the mean in practical scenario. Okay. Now, till this particular time, we had talked about something, as I told, it's called the univariate situations. That means there is only one variable, either x or y or something else, and we are finding out in terms of that particular number. Now, after this, what if the situation comes into there are two sets of variables, and typically we are finding out a set of x and y, and this particular set is called the bivariate data. Application, what is the meaning of this bivariate data? So suppose say for few years, say 1960, 1970, 1980, 1990, some years, you got a say cotton input and cloth export. Right? Could be 12 values. So cotton input I'm telling it is X, cotton cloth export here I'm saying is Y. And on the basis of these two parameters, I can get few numbers, of course, some units, some numbers. I can generate, I can find out some numbers. I can find out. So this could be any numbers. Right? So given that a situation, given that another times or typically the time series data, depending on the time, if you have defined two different variables, that particular set of data is called the bivariate data. Now the thing is that is always our assumption, our question would be that how these two data are connected to each other. So like if I just drop this into the axis, this is the x-axis, this is the y-axis. So suppose x-axis follows the cotton import and y-axis follows the cloth export, right? So of course this itself, each and every number are one point in this particular xy plane, right? So if this is the case, then of course we can find out that what is the degree of connectiveness between these two parameters x and y. To find out this degree of connectiveness between the two parameters x and y, we generally find out something is called the correlation between these two. Now, before correlation, of course, there is a this correlation depends on something. That something is called the covariance. So variance, of course, from one particular set of variables, that how the data is bifurcated from the mean. In this particular case, we try to find out the bifurcation from the mean itself, but from the in terms of the two sets of data, because you got x values and the mean is x bar, y values the mean is y bar. Now I need to find out in terms of both the cases if I want to simultaneously, if I can find out that how these numbers are away from this variance, this numbers. So in terms of the both the parameters, that particular parameter is given by the covariance. So it is given by this. Now, since it is we are not dealing with a single xi minus x bar, a single yi minus y bar, so this particular parameter may not give you a zero, always give you zero. So that's why the square part is not there. That's why the covariance looks something like this. Of course, if you simplify this, let me simplify this a little bit. So as I told again, this particular equation is for the algebraic kind of situations, and the simplified version would be for the mathematical equation. So if I just multiply x y minus xi y bar x bar y and plus x bar y, right? I'm just multiplying, I mean it's basically just multiplying this, and then I'm putting all the summations to everybody. So now of course the y bar, x bar, these are constant values. So it is if I just put this take the y bar out because it's a constant, so the summation is not going to help you there. So I just put 1 by n summation of yi, and then x bar is outside. And in this case, we had done this before, but let's try it also. So 1 by n constant, it will be n into x by y bar, and then n will go back, so it will become an x bar into y. This nothing is going to change because to keep stay same. This is X bar Y bar. This is again X bar Y bar. This is X bar Y bar. So gone. So finally, this is the simplified version of the this equation. So both the equations are correct. So again, as I told, this is for the algebraic purpose. This is for the mathematical purpose. And in the numbering, the number kind of problems, if I come in, we generally use this formula. But this is the covariance. Covariance, of course, gives you the idea how this x bar and y bar is connected to each other, but it does not give you any kind of another indication, like how they are connected in terms of, say, what is the directions of the connection, uh, and all this kind of thing. That does not give you the covariance, does not give you that kind of information. So to do that, to further normalize this particular covariance concept, so for the correlation, we find out using something is called the correlation coefficient, that is given as xy. If it is a correlation coefficient between the two variables x and y, it is called the r suffix xy. It's given by x covariance of xy divided by sigma x by sigma y. So this is the formula by which we can actually find out the covariance numbers. Now, what is the significance of this particular parameter? Of course, see, when we are finding out the covariance coefficient, correlation coefficient is very unique coefficient. Of course, there are different type of correlation coefficients are there, Pearson's, and some other names are there. I'm not going there. I'm making it simple. So, what is that? Does it signify? This particular coefficient does signify the pattern how the x and y are basically connected. Suppose x and y are connected something like this. So this is a data point. So as I told, the data points we can put and drop, drag and drop this here. It should look something like this. So you can estimate, you can at least find out that the parameter is going something like this. In this particular case, the r is positive. Right? What is the meaning? That means that if the x is increasing, y is increasing. If x is decreasing, y is decreasing. And if I assume one straight line, any straight line from this particular part, the slope of this particular case would be positive slope. Right? In this particular case, this is called the positively correlated. So typically 0 to 1, any number you can think of, this comes under this particular scenario, that is the positively correlated situation. Similarly, if you see something like this, where you can assume a straight line again, where your increasing of x does shows that decreasing of the y. So that means that it is negatively correlated. So increasing of x shows the decreasing of y, or the decreasing of x shows the increase of y. Of course, you can see from this graph. So this particular line, of course, if you find out, this graph is a negative. The slope is negative slope. So from 0 to -1, this correlation value generally comes. So this is called a negatively correlated. Third case would be if there is no concrete pattern between x and y, and the increase or decrease of the x and y does not gives you some any kind of pattern on the terms of the other parameters, then that particular uh, set of data is called the uncorrelated data, where typically r is equal to 0. Of course, in this particular equation, you can see that x and y cannot be 0, sigma x, sigma y cannot be 0, then it will be infinity. So typically, if ry is equal to 0, that means that the covariance of this xy is generally 0. This is called the uncorrelated data. So this particular parameter, which is a no unit parameter, that gives you that idea that how these parameters are connected and which directions basically it is connected. And of course, we can see from here that it has a specific value between minus 1 to plus 1. So your correlation value cannot go beyond these numbers, minus 1 to plus 1. Of course, if you're getting some numbers rather than these numbers, that means there is some error in the account. Typically, R is equal to 0 gives you the um, uncorrelated value. So this is the main very important parameter in terms of, like, suppose in some situations, say you got to say like this export input data, right? In general, for the say last 20 years, you are getting the export input data as say positive numbers. So you are getting simple, just the simple correlation coefficient you are calculating, and you are getting the positive data, which is a standard pattern that will be given that how much you are getting as a um, any your basic items you are getting, you are importing, and the things you are exporting, which is far more than that, then it is a positively correlated. So of course by default you are getting. So some point of time, suppose you got the as a negative correlation, so probably your correlations points are basically dropping. That kind of a basic indications that your business is going to get hampered. Right? So this kind of small parameters can give you the idea on depending on the set of data that okay, this is situation is not good, or situation is something we needed to take care of. This kind of situations may happen. Okay? So these are the parameters we should can take care. Of course, this correlation coefficient later in the next section, that is the regression part. This will take care and will also play an important part to create the equation. Of course, the another parameter, regression parameter, is there, which is depends on the correlation parameter. Now, of course, as we are discussing about the change of skill, change of origin every point of time. So let me just give you the idea what will happen if we do the change of skill. Sorry, so we start with the origin. Change of origin, that means that here, of course, we have already used the x and y, so we use the u and v. U say x minus c, and v say y minus t. Both c and d are the constant values. If this happens, that means so we need to find out the covariance, because we have two parameters now, covariance and the sigma and sigma y. So what will happen in terms of sigma u and sigma v? What will happen? Covariance of u v. So this case it will become ui minus u bar, vi minus v bar. So what will be happening with the ui? So ui will be nothing but xi minus c. U bar will be, of course, u bar minus c, right? So this is I just write here. So u bar would be x bar minus c, and v bar would be y bar minus d. Okay? So x bar minus c will become plus. Here it will become yi minus d minus y bar plus d. So if it is 1, that means 1 by n xi minus x bar yi minus y bar, which is nothing but the covariance of xy. So change of origin does not hamper the covariance. And already, if you remember, the change of origin does not hamper the sigma also, the standard deviations also. That means that R u v, that is covariance of u comma v by sigma u multiplied by sigma v, is same as covariance of x comma y sigma x multiplied by sigma y. That means the RXY. So it is not going to change. If you do the only change of origin, there is no difference into the RUV of, and neither it is changing the covariance nor it is changing the correlation coefficient. Similarly, if we take the change of scale, so let's take U is equal to x by c, and v would be y by d. Both c and d remain constant. So ui would be xi by c, vi would be yi by d, and u bar would be x bar by c, and v bar would be y bar by d. Okay. So now let's again put in the same formula for the covariance u comma v, right? And by the expression I compare ui minus ui, vi minus ui. So we will just doing yi minus t y by t. This would be x, right? This would be x by c. So I just do that. It will become x I by c minus x bar by c, and this would be yi by t divided by y bar by t. So I need to take out the constant values. Let's take c and d outside. It will become 1 by n xi minus x bar yi minus y, right? So 1 by c multiplied by d to become covariance of x comma y. So covariance of u comma v 1 by c multiplied by. So basically here we are changing. If we are doing the change of scale, covariance is going to change. But the thing is that if we can remember, sigma u is going to be a sigma x by c, and sigma v would be sigma y by d, as we had just done before. Here is not change in the change of scale, change of in the change of scale. Your sigmas get affected by this. So if I find out finally RUV, we just put the values. So variance x comma y by c multiplied by t, sigma x by c, sigma y by t. So these are gone. Covariance of x comma y by sigma x sigma y. That means so so that means although my covariance is changing, but finally the correlation coefficient is not changing also in terms of the change of origin. So during the calculation of the correlation coefficient, specifically correlation coefficient, you do whatever addition, divisions, multiplications, anything with the parameters, and change of the scale and change of the origin. If you do anything on this particular scenario, your final numbers would be same for any cases. Of course, your covariance would be different. Of course, since this the situations you are getting, but eventually the correlation coefficient is not going to change depending on your change of scale and change of origin. So that would be fixed. We'll show this in terms of the problem. So typically there are two types of problem statement problem you can find out in this particular case. So one type of problem is straightforward. They generally gives you the summation values, not the table. And then the second portion is the more typical, that is the table part of the table. So that is first is I 1 to 100. Summation x is given as 280. Summation of 1 to 100. Y is 60. Summation of 1 to 100. Of course, I 1 to n is already here. So x I square should be 2384. Summation of 1 to 100. Y square is 117. summation I want 100 xi yi is 438. So find the correlation coefficient. Yeah. So these numbers are given. You need to find out the correlation. Of course, this 1 to n is already given. So that means that by default in this particular part they have given the n is equal to 100 from there. For this case, of course, in many books you will find out a big equations are there. You can always use the equations, but I generally prefer to go step by step. So if you are doing any kind of calculation mistakes, you can easily find out that. So since I have to find out the covariance of sigma y by sigma x and sigma y, that means that I need to find everything step by step, because in the covariance I got the x bar y bar and sigma x sigma y. Anyway, I have to find out the deviations in both the cases. So I will find out all the parameters step by step. So if I say suppose find out the x bar would be 1 by n of summation of I1 to n xi, that is nothing but the 280 by 100, that is 2.8. Y bar would be 1 by n summation of I1 to n yi, that is 0.6. Now sigma x square, that is 1 by n summation xi square minus x bar whole square. So numbers are given there. So 2384 by 100 minus 2.8 square. To simplify this, we should get 16 sigma y square. So 1 by n summation I1 to n yi square minus y bar square. Right. So this is also given yi square 117 by 100 by 0.6 whole square. So this has become as a 0.81. So then the basic parameters we have calculated. So we can now find out the covariance, the last parameter, that is again summation y1 to xi yi minus x bar y bar. So this is also again given. So number is 438 100 minus, this is 2.8 multiplied by 0.6, right? So please, 100 is only with the summation xi yi, not the whole numbers. So many calculation mistakes happens because of that. So if we simplify this, it should be 2.7. So I got the almost all the numbers, but make sure you found out the variance is there, not the standard deviation. In the equation, there is standard deviation, not the variance. So make sure you put the square roots there. So Rxy would be 2.7 divided by square root of 16 and square root of 0.81. So come 4 into 0.9 is 0.7. So it is highly positively correlated. It is going towards +1. That means that this data, whatever it is given, that is positively correlated. So this is one type of a problem where the typical numbers are not given, but eventually using the summarized data, we can find out this. Now the next type, that is, we have given you some set of x and y table, and from that particular x and y table, we need to find out the standard deviation, the collision coefficients. So for that, how can I do? So let's try to put the table together. It's better to take the page. and given like this, some numbers. I'm not even not putting the story like what are the, this is some indicators of some business or some. So I'm not even putting the story. So that we put in sentence 66, 67, 68, 64, 65, 8, 69, 62, 66, 70, 68, 66, and 65. 1, 2, 3, 4, 5, 6, 7, 8. Yes. So suppose these numbers are given for the two sets of parameters, and the somebody asked you to find out this. There is a what is the collision coefficient between these two parameters. That is the parameter x and parameter y. Now, again the same thing. We can use the straightforward these numbers, but since we know that if we do a plus minus or do anything in terms of in these parameters, if we change the parameters, your um, collision coefficient is not going to change. So I can do anything in terms of this cases. So say making say u, that is x minus 65. Now these numbers are not any universal numbers. You can choose as per the given numbers. This is I'm putting as minus 67. So that particular number may not be coming from exactly this number. See, for x 65 is there, but for y 67 is nowhere there. But from the empirical way, you can find out which number. If I just do a minus, this gives me a quite small numbers. Could be a kind of a median number from there. That could be a median number. It could be a some number which is gives you the quite a small gap in the terms of the other number. So that is up to you. Whatever number you are going to choose, this is whichever makes your life easy, and choose that kind of a number. There is no hard and fast rule that you are going to choose any such kind of a number. Minus 2, this is 2. So the first column minus 65 doing here. 2, this is minus 1, 3, minus 3, 5, and 1. Okay. This is my new variable u. Next new variable v should be 1, minus 1, 1, minus 2, minus 1, 1, 2, 5, 6, 1 minus 1, 1 minus 2. The 2 should be there. Minus 2, 2, 6, 9, 6, 7, 2, yes. 2 minus 1, 1 minus 2. So I put the two new variables. So this is the required. What else I need? I need the u square, right? U square for the variance purpose. So I'll just u square of this particular column. So 0, 4, 4, 1, 9, 9, 25, 1, right? And for the v square, 1, 1, 1, 4, 4, 1, 1, 4. So that is the beauty of making the things quite small. And finally, I need the UV to find out the covariance. So, third and fourth column multiplications. 0, 2, 2, 2, 6, 3, 5, minus 2. Okay? So, be careful about when you are doing the plus minus thing, at least for the covariance part, plus and minus is very important. So, what are the things I need? I need the summation for the finding out my sound mean of u. So I need this. So that's why it is 5. So this is nothing but please keep writing here. is my summation rule. This number is minus 1, is nothing but the summation of v. This number is nothing but the summation of u square, that is, I guess, 53. This number is summation of v square, that is 17. And this number is summation of uv, that is 18. So I got all the numbers. So let's find out. So x bar I will keep in terms of the fraction numbers to be helpful for you. So 1 by n summation of is u bar. Ui. So ui would be 5 by 8. V was simply, I'm not writing the formula. So already have written a of times. So minus 1 by 8. Sigma u square would be 53 by 8 minus 5 by 8 whole square. If you simplify and keep this as like this to come something like this, you can go for the of course fraction, that is obviously. So by 8 minus of minus 1 by 8 whole square, it is coming as 135 by 64. And the last one, we'll get the covariance one. Covariance uv would be this number 18 by 8 summation of uv, this number, minus of this little bit tricky because one of the number is a negative number, so it will eventually become a positive number. So that's why covariance is a little bit seriously to calculate. So this will become a positive number. If you can eventually place this, it will come as a 49 by 60. So now if I put the RUV would be sigma mu sigma v like 149 by 64 divided by square root of 399 by 64. Eventually, it is not going to help me that much anyway. But again, like if you do the approximations, like you can make it as 400 by 64. That would may help you. But not the next one. 135 by 64 again. So eventually, it will get something like 640. And since, as I told, there is no change of the correlation coefficients due to the plus minus or division and multiplication of the parameters. So whatever number you are getting, that is the value in terms of the correlation coefficient. So that's how this is the process. That's how you should follow the equations. Right? That's how you follow the step by step. Of course, this kind of problems are there. A lot of problems like this, so you can practice like this way. So this is the correlation coefficient. So with this, let me give you two formula. In many places you will find out the applications and a little bit algebraic kind of advanced problem statement. So suppose two variables are there. So two variables are there, x and y, and we can define another new variable, say z1 x plus y and z2 as x minus y. This is also variable. This is also two sets of variables. So we are adding and subtracting those two sets of variables. Right? So if that is a scenario, then if I need to find out the variance of x plus y, how can I find out that? Of course, this is a if you just put into the formula and if you expand this, eventually you will come up to the this formula. So I'm not showing the derivation. but you can keep this formula with this with you if you later thought if you go for the depend sorry joint probability and the conditional probability situations, this is going to help you a lot. Same this kind of stuff. So variance of x, variance of y as to covariance of x comma y. And similarly, variance of x minus y would become variance of x, variance of y minus 2 covariance of x comma y. This is a two sets of formula you can give, and let me show you. And of course, this covariance, there is a covariance is there. I'm just if I just want to show in terms of little bit complicated. If I just want to write, if I of course covariance can be written in terms of the collision coefficients, right? So I can write 2r sigma x sigma y. So typically, almost all the parameters in terms of the variance I'm writing sigma x square plus sigma y square minus 2r sigma x sigma y. So either way you can write in the like from covariance, it is quite easy to write like this. Okay? So this is the formula basically with the variance of x plus variance of y. It is for the variance, not the standard deviation, of course. Variance only. You can derive it. It's very easy. So variance of x plus variance of y plus 2 covariance of x y. If you want to replace this covariance in terms of the collision coefficient r into sigma x into sigma y. Right, that's it. So let's take a small example and understand how this particular formula can be useful. Say if we correlated variables x1, x2, and x3 have same standard deviation, and correlation coefficient between x1 plus x2 and x2 plus x3. So that two variables, as we have defined previously, z1, z2. So just so problem is saying in the first line, of course, there is a lot of information is given. So if three uncorrelated variables x1, x2, x3. So basically x1, x2, x3 is uncorrelated variables. First thing first. Second, they have the same standard deviations. That is also another information. Then they are asking the collision coefficient between the x1 plus x2 and x2 plus x3. So I need to take this as a two other variables, two new variables. So let's say u as a x1 plus x2 and v as a x2 plus x3, right? So I need to find out the R u v. Now the important part, given that what are the information I will give? Given first thing is that three variables are uncorrelated. That means that if you of course the uncorrelated variables three cannot be together. So that means that if I take all the possible pairs in between these two cases, those are uncorrelated. That means that R x1 comma x2 is equal to R x2 comma x3 comma R x1 comma x3 all should be 0. That is the meaning of the uncorrelated, right? As I told that the sigmas, the sigmas are not 0 because it is telling that is the same sigma is there. That means that some numbers are there. So that means the covariance part has to be 0, right? So that means that covariance of x1 comma x2, covariance of x1 comma x3, and covariance of x2 comma x3 are 0. Of course, covariance of x1 comma x2 and covariance of x2 comma x1 both are same anyway because summation, sorry, multiplication, right? So it is same. So covariance of x1 comma x2 is equal to covariance of x2, sorry, x1 comma x3 and covariance of x2 comma x3 all are 0. So this is the line number 1 basically is giving you the ID, the output variable name. Now second is telling that both all they have the same standard deviation. So let's write that. That means that is equal to sigma x3 is equal to sigma. Let's say it is sigma as well. Some number sigma. So these two things are given. I need to find out the R U V where U is equal to x1 plus x2 and V is equal to x2 plus x3. Now let's start from a very basic definition of the RUV. So if I want to find out the RUV, what should I find out? Covariance of U comma V divided by sigma U multiplied by sigma V. Correct? Now let's start with the simplistic one. That is the denominator. That is sigma U and the sigma V. Let's start with the variance. Gives you the better idea. Better, of course, the formula because already have done formula, right? So sigma U square means that the variance of U. What is the variance of U? As I assume that variance U means x1 plus x2, right? That's what U is, variance of x1 plus x2. Similarly, variance of V would be x2 plus variance of x2. Now, if I use the previous formula, so sigma U square is plus x2. That means if you put the formula variance of x1, variance of x2 plus 2 covariance of x1 comma x2. Now what are the key things given? Variance of x1, that means it is sigma square from this line, left and right. Similarly, variance of x2 is same, sigma square. This covariance is already 0. We have so this is so it is. Similarly, if you find out the sigma v square variance of x2 plus x3, that means variance of x2 plus variance of x3 plus 2 covariance of x2 comma x3. Same thing, covariance is 0. These are the sigma square values. Sigma square plus sigma square again 2 sigma square. So two things denominator is done. So I got the sigma u square and the sigma. Fix on the find the covariance part. Covariance u comma v. So again we start with the very basic definition. Since we are doing the algebraic part, so we'll define the u minus u by u by v minus v bar. What is u? So ui minus u by vi minus v. Right? So what is x1 plus x2? If I write the ui, that means x1I plus x2I. ui would be x1 bar plus x2 bar. Similarly, v would be I would be x2I plus x3 and v bar would be x2 bar plus x3 bar. Now put this into this formula. So it will be delicate. So let's put x1I plus x2I minus x1 bar minus x2 bar multiplied by x2I plus x3I minus x3 bar minus x2 bar minus x3 bar. Now, of course, some pattern you can already you can see here. So if I try to take this together, x1I minus x1I minus x1 bar plus x2I minus x2 bar, right? This is in the left hand side, and the right part would be x2I minus x2 bar plus x3I minus x3 bar. So you can see there a plus b multiplied by b plus c. That is basically is happening. Now what if we multiply this? It will be the perfect to find out what is going on. So basically I'm going to multiply it by this a plus b plus c. Of course, one b square will come into the picture, and all the a into c, b into c, and a into and this is yeah, that is will come. A into b will come. So let's do it, and we'll put all the 1 by n summation to everybody. So let's do that. 1 by n summation I1 to n x1 I minus x bar multiplied by x2 I x2 bar is the first one. Second would be 1 by n. So this multiplied by this I will do now. x1 1 I minus x1 bar x3I minus x3 bar plus second, now this multiplied by this. So 1 by n summation I1 to n xi1 sorry x2I minus x2 bar whole square, and the final one is the 1 by n x2I minus x2 bar multiplied by x3I minus x3 bar. Now what are these things? If you concentrate on this particular thing, it is nothing but x I minus x bar y I minus y. That's that particular pattern. That particular pattern is also here, also here. This is nothing but the covariance of x1. This is the this one. Second one is covariance of x1, x3. I'm keeping this part. The last one is the covariance of x2, x3. These three things are the covariance. And what about this? This one? This is nothing but the variance of your x2. So this is variance of the x2. And if you remember, these are nothing but 0, 0, 0. Only the variance of x2 is something as a sigma square. It is a sigma square. So of course now we got the both of cases. So our UV would be covariance of UV divided by sigma U and sigma V. So we have found out the covariance given as sigma square and sigma U as root of 2 sigma square, and this is square root of 2 sigma square. So sigma square by 2 sigma square eventually. So this kind of a algebraic kind of problems you may face in the graphical scenario. So this is the more or less the process how we can deal with the correlations. Now the limitation of the correlation is, as I told in terms of the graph, that suppose things are positively correlated, the assumption is that the points I got x and y, I'm getting a positively correlated kind of pattern in terms of this particular pattern I'm getting here. Say R is coming towards a point, say 9, something like that. You are getting something. Yes. Okay, so I know that okay, if x is increasing, that means that y is also highly increasing. I mean, like the same rate x is increasing. Basically, I can write if x increases, that varies that y is also increases. Like this, I think, right? So almost it is a 1:1 scenario. That's how basically it is. I mean, of course, if I just write x is equal to some k into y, I can write k into some constant into y. It is basically varying. If that is the scenario, but the problem is that if x is increasing, y is increasing, this particular statement gives you the directions that okay, that is the direction, that's how basically your parameter is increasing or decreasing, but that does not give you the exact amount of number. Okay, suppose if I take the x as a say value as 50, can you tell me what is the value of y? Or say y is as a value of 30, can you tell me what is the value of x? Or probably in future, which is not there in this particular parameter, in this particular scenario, if the say the x is coming as say 200, some point of time it is coming as a 200, can you tell me what is the value x y should have? If that kind of scenario comes into the picture, that kind of questions comes into the picture, the correlation coefficient, this R, cannot give you that answer. Okay, there is a limitation of the there is a limitation of your correlation coefficient, that it does not give you the specific answer of the given value of the x to y or y to x. So of course, typically there is no as such. I mean, R does not specify any kind of a model between this set of points, that how these particular points are connected. So for that, we came up with another concept, something is called the regression. So regression, of course, it proposes equation in terms of this set of data, these sets of points, in terms of this correlation parameter, that okay, how this x is changing in terms of y. Can I provide you some kind of a model that okay, using that particular equation, number of x, can I estimate the number of y? Of course, I'm using the word estimate because the estimation theory and the regression has a quite a good connection. So probably for the first this part of our discussion, initially I'll keep the regression line as a simple discussion, but eventually we will reach end of our discussion. We'll come back again to the regression problem, and we'll discuss more about the regression part. So the regression itself, this particular topic, we are going to discuss two times. The one is the first part would be simple one, second part would be the complicated one. So typically we are assuming there we can put some kind of a regression model, so which can tell me that given that if it is a x is changing, y is also changing on the basis of this kind of a number, how that is basically changing, and if can I provide a specific equation or the specific model. Now, type of regression, there are two types of regressions are there. One is called the simple regression. One is of course the multiple regression. For the meaning of this, simple regression is that there is a though this little bit a hypothetical situation that suppose your one variable is there and the particular variable is only connected to this particular variable x. Okay, there is only not one sided, it is both sided. So if I know the if there is a y variable is there, it depends only on the another variable x, or x is a variable there which depends only on the variable y. If that is the situation, that is basically is called a simple connections between those two parameters. There is only one set of axes are there, where say suppose sales and profit in a company, particularly your sales depend on the profit. If sales increases, profit increases. If sales decreases, your profit decreases. If this is a scenario, then you can say it is a simple regression model. There is a simple regression model. Now, of course, in reality, that does not happen. Of course, if you have a one variable, it depends on a lot of parameters and so on. So, if you are talking about, you are thinking about in terms of the machine learning problems. So in the machine learning problems, you know that okay, given that this is a car, I have say a bunch of a lot of parameters. On the basis of the particular parameters, I want to describe this particular variable. That is a car. This is a typical this is a particular car. I'm going to basically in terms of the class car, I am going to describe in terms of a lot of parameters. These parameters are nothing but this your x. So basically if one variable is connected to the multiple variables. So that multiplicity access will come into the picture. So this is the simple and the multiple variables. Of course, multiple variables part may talk in the estimation theory. If the time permits, we'll talk a little bit about the machine learning situations and how the regressions we take care of that part. So all these things we'll talk there if it is possible. I was wondering, its initial stage, let's take this as a simple regression model. Simple regression model is straightforward. You got a 1:1 situation, y is versus x. So, if that is the case, again, there are two types. Something is called the linear regression model and non-linear, of course, model. Linear regression model is this, what I'm talking about. X is versus y. So typically, for the simple linear regression model, if I say simple linear regression model, that would look something like this. Y is equal to say beta 0 plus beta 1 x. Right? This is a standard process you have to write this equation. So it looks something like this. So given that a lot of points are there, somehow I have found out this particular line equation. How we have found out, we'll talk about later. So assume somehow we are finding out this particular line where this constant value is mainly given by the beta 0 and the slope of this particular line is nothing but this beta 1. This is that's how basically we are creating this particular line. So y0 beta 0 is the y-intercept that respects that. Basically, suppose I am doing this particular experiment a lot of times, so I am getting that at x is equal to 0, I am getting a lot of y value, and after that a lot of y value, I found out mean of the y value. So y bar I find out on the basis of that y bar is nothing but this beta 0 basically. Right? So average of this y bar is basically the beta 0, and of course some other process are there on the basis of that particular process. If I find out the slope of this particular line, then the straight line equation is can be given by this equation. Okay. Now, of course, that line does not mean that all possible points are going to be on the top of that particular line. That would be an ideal situation. That does not happen anyway. So, what happens in generally, assuming I am assuming this particular line is there, so the observed value is something like this. I am estimating that something. This is the point. So estimation part is on this particular line, right? So there is an error between this. This is the error coming into the picture. This is the error. So it really says as a residue. Okay. So typically our line comes like something like this because you beta 1x with the error or residue, what we want to say. This is it like this. Our main motto stays there. So of course, from the one particular point, I am telling this. For all the points, of course, I will get a lot of A1, A2, A3, A4, like a lot of numbers I'll get. So our main motto would be to minimize this particular number, and that is how basically all the estimation theory, all the basic calculations, how we should calculate this um, model that comes into the picture. Okay? So that is the way how we should deal with the basic linear regression models. From there, we can go to the complex process, complex compound process, and everything we can go. So this is a basic linear regression, simple linear regression model. What is a non-linear regression model? How should it look like? So, of course, if it is a non-linear regression model, it should look like something like this: beta 1, x1. Okay, so let's put it as x only. Beta 2, x squared, beta 3, x cubed, and so on. Depends on what type of variable. So, this is a beta. All this beta is basically called the partial regression coefficient for the. And if I just put as x1, x2, x3, then it will become a multiple non-linear regression model. So of course, you have all advanced linear, all advanced regression models actually comes under this particular scenario. So this is the basic. This is the basic of the linear model. As I told, we'll start our estimation theory probably from this particular equation. Since we don't have much time, just to give you one last set, that is, as you know, this is the simple linear model. So for the first half, we are going to discuss only about the simple linear regression model. So for that, with some lot of calculations, lot of things happen and some things. After that, we have found out. So for the linear cases, if the y is the dependent on x, so y on x, that's why it's called the y on x. If that is a situation, then the formula generally comes out as a y minus y bar is equal to b y x minus x bar. X by y bar, obviously the mean for the x and y, obviously. In this case, x is a known variable, y variable is dependent on you. Suppose if somebody asks you, okay, so I got a 6 weeks sales value, what could be the estimated value of the 7th week sales? In that particular case, that sales value is your x, and the y is the weeks is the your dependency. So 7th week, basically 7th week you want to find out. So these weeks are the x value, and unknown variable that the sales is the your y value. In this case, this is the pyx is the parameter that is called the regression parameter. It is y on x. That is the meaning of this regression parameter. And similarly, if the equation is x on y, so it will become x minus x bar, the xy, y minus y bar. Here the parameter is called the. So of course, how this equation came, there's a lot of derivations and everything are there. So we are not going to a derivation part, but from how from the basic equation of this particular situation comes up, we talk about the regression analysis process, right? So regression analysis in terms of the estimation theory process, and of course there are a lot of parameters are there, p values and all other r values are there. Some very important parameters are there. We talk about those parameters that point of time, because otherwise this particular, there is some concepts are required for the sampling theory. So that's why. So we divide this concept in two different parts. So this is the two equations. So we'll talk about these equations more in the next class. Of course, I'll introduce the equations one more time, and then how to deal with these equations, how to find out these parameters, and how this is connected to the collision coefficients. That all the things we will discuss in the next class. So that's it for the today. So please read about. You can choose any standard book. I generally follow the book called In Das. If you can find out the book, so just write it here. So
Sir,
In Das book.
sir, it would be really great if you could send an email related to the books that we could refer, like.
Sure, sure. I'll share that. I'll share the mail.
Yeah,
Okay.
thank you.
I was going to tell this is the book I generally follow, but it has two types, but not the Tata Manual one, the older one, and that is
Oh,
called Statistical Inference. That is a book, and one J.K. Agarwal is also there. Anyway, I'll mail this. So these two books are quite very basic, and you can follow. And whatever I'm teaching, if you're in future you are teaching also in statistics, probably you can take help of these two books. These are very very basics. They have given all the possible examples, step by step, all the derivations and all everything are there in these two books. So you can take help from there. Anyway, after this and probably the next class, the regression would be done. I'll share the notes as well as the assignment one after the third lecture. So we'll get the notes as well as the assignment after the next lecture. If you have any questions, please feel free to mail me. So this is my mail ID.
okay, sir.
So anyway, you'll get a mail from me about the book list and everything. This is the mail ID. If you have any questions or if you want any details or not details or whatever suggestions if you have, please feel free to mail if you're not telling here. You can tell me here now also. Okay, fine. If you have nothing there, then I can stop it today and see you next week.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
You